All right, we'll get started. So today we'll be talking about magnetism. So from today on, for the next couple or more weeks or so that will be the main focus, the main topics in this class. Okay, so I think a lot of you guys know what magnetism is. So basically, um, magnetism is caused by current going through a wire. So it's actually related to current. So when you have a current, you actually have a magnetic field surrounding it. Okay, so that was first discovered about 200 years ago by the Danish physicist Hans Ørsted. So what he discovered is once he closed this um, switch of the circuit, and when there's current going through there, then this guy, the compass here will turn, indicating there's a new magnetic field generated by this current. Okay, so it's really that's the origin of the magnetism, the current. So you can imagine for magnetic materials which has magnetism is because there's inside the material for each atoms there's actually ion, the electrons orbiting around the nucleus. So which if more electrons are orbiting in the same direction, they create a net force or the net current in that sense. Then the atom will produce a magnetic field. And if many atoms line up in the same direction for the magnetic field they generate, then the material will have magnetism. Okay, so basically, magnetism is due to the current in the region. All right. I don't know about you guys, but my kids, they like the magnetic blocks very much, so they can use them building different structures, and they fight against each other for that. But if you have used them before when you are kids, you know how they works. Okay, so basically, for a material that has magnetism, it has actually two poles, a south pole and a north pole. So this is very similar to charge. There are two types of charges, positive charges and negative charges. So the same thing for the like poles. If you have like poles close to each other, they repel each other. If you have opposite poles close to each other, they actually attract. Okay, so that's the same as charges. This is a little bit different here for magnetic material. For a single one, you will have a south pole and a north pole at the end. But you can cut the material, you can divide it into small pieces. Each time you cut it into new pieces, the new pieces will have a new pole generated. So then it will also now again have a south pole and north pole. And then for the other piece, that's the same. It will have two poles. Okay, unlike if you have a object that have charges, if you divide into two, no new charges will be generated. Okay. Now you can keep dividing this into small pieces. Each small piece will have a south pole and a north pole. Okay. The Earth itself has a gigantic magnetic field. So where the geographical North Pole is the South Pole, or it's close to the South Pole of the magnetic field. Okay, not exactly line up. So in that sense, if you use a compass, you want to find the North Pole, geographic North Pole of the Earth, you will be off about 2,200 miles. Okay, off of the actual geographic North Pole. And so this is South Pole, so if you have a compass, right? So then its North Pole will be lined up with that because opposite pole actually attract each other. So that's how a compass work, but not exactly to the north. Okay. The Earth's magnetic field actually has reversed a few times throughout the years. That is, by study reveal that. So on average, it takes like about any time. It doesn't like follow a consistent pattern, but sometimes between like 0.1 million years, sometimes it happens every for a million years. Okay, so but the average is like about 450,000 years. Okay, so the Earth's magnetic force will reverse. Okay, and the time it takes to reverse lasts about 1,000 to anytime between 1,000 to 10,000 years. Okay, so if there's one coming, then it will probably disrupt our compass system or maybe GPS system as well. But we haven't seen that happen yet. Okay. Magnetism also has a lot of applications. So these days we are using cell phones, laptops, and all these electronic devices. And most of them have like a storage disk inside. So the storage disk is made of magnetic materials. Okay, so in that case, we need to have a deeper understanding to do the design of these disks. All right, so let's talk about the strengths of the magnetic field. Okay, so as I mentioned earlier, when you have charges moving that create current, then there's magnetic field. So the magnetic fields are created by moving charges or currents. So in that case, if you have then a charge that is moving inside the magnetic field, okay, so you can imagine then that charge will probably produce a current, and then the current will produce a magnetic field. The magnetic field actually then will interact with the existing magnetic field. So there's interaction between the charged particles and the magnetic field. So the magnitude or the force that the charged particle experience in the magnetic field, this is an experimental result. It's proportional to the charge and proportional to the speed of the charge, proportional to the strength of the magnetic field, the external magnetic field, and it's also related to the angle that the velocity of the charge makes with the magnetic field. Okay, so that's a sign of the theta, the angle the two makes, the V and B makes. So magnetic field is also a vector. Velocity is a vector. Magnetic field is a vector, and just similar to the electric field E. Okay, for the magnetic field. So this is the magnetic force particle experience. So you can see it depends on what angles, right? So, and then also the velocity. So if the velocity is zero, then the force will be zero. If the angle is equal to zero, that means if B field and V are parallel to each other, you'll get zero force. The maximum force occurs when the V and B makes an angle of 90 degrees. In that case, sine of 90 becomes 1. 1 is the maximum of a sine function. Okay. So we use this, we can actually back calculate what will be the magnetic field. Okay. If we know the velocity and the charge of the particle and then the angle, the velocity and the magnetic field makes. So magnetic field can be back calculated by using the force that you can measure and then divided by the charge, absolute value of it, velocity, and sine of theta. Okay, so magnetic field then is represented by symbol B for the quantity of magnetic field. It has a unit of Tesla. You guys heard about Tesla, right? So yes, the car Tesla gets the name from the units of magnetic field Tesla, and the unit of magnetic field Tesla comes from the scientist Tesla. Okay, so 1 Tesla or T for the abbreviation for the unit is equivalent to 1 Newton over amperes times meters. Okay. All right. So because there's a sine theta here, so if you go back to the force, F equal to Q, absolute value of Q, VP sine theta. So then we know that if you have two vectors, V cross B, actually it gives the magnitude of V times B times sine theta. So the force is really coming from the cross product of the velocity of the charged particle and the magnetic field and times the charge of the charge as a scalar. Okay, so cross product of two vectors result in a vector. So F equal to QV cross B then. Okay, so let's take a look on this example here. It says an electron is projected into a uniform magnetic field, point phi in I direction, point A in K direction, in the unit of Tesla with a velocity of 3.0 I plus 4.0 J, 10 to the 6 meters per second. What's the magnetic field, magnetic force on the electron? Okay, so it's asking for the magnetic force, which is a vector, right? So that means we are looking for a vector we can use actually the we can so the magnetic force. Okay, so the magnetic force. So we can use the cross product of V and B. So F equal to Q V cross B. Okay. All right. So we are looking for force. And then F is equal to the charge times V cross B. Get it back, better focus on this. All right. So we have V, that is 3.0 I plus 4.0 J times 10 to the 6 meters per second. We have the B field, which is 0.5 I and then 0.8 K in the units of Tesla. Okay, so for the electron, E is a constant charge of it. So Q is equal to E, that is minus 1.6 times 10 to the minus 19 coulombs. Okay, so then this equals to minus 1.6 10 to the minus 19 coulombs. V cross B, 3.0 I, 4.0 J, 10 to the 6 meters per second, and cross product of the 0.5 plus 0.8 KT. Okay. So typically, if you have three components x, y, z, cross product x, y, z, and if you remember what's the result, you can just directly do that. But this is only two components here. Okay, both of them. So you can just use the distribution on multiplication. So this guy goes in, right? The 3.0 I, and then goes in there. This guy goes in there, and this goes in there. So you'll get like four terms, but we can put this in front. So this will give you minus 1.6 times 10 to the minus 19 and positive 6. So that gives you minus 13. Okay, coulombs times meters per second. All right, and 3.0 times 0.5, that gives you 1.5, and then you get I cross I for the first one, plus this guy times that guy, 2.4, 3 times 0.8 is 2.4, and you have I cross K. Okay, now 4.0, it goes into the parentheses, so that becomes 2J cross I, and plus 4 times 0.8 becomes 3.2 J cross K. All right. So for the cross product, if you have I cross I, that will give you 0. Okay, because I and I are in the same direction, so it's 1 times 1 times sine of 0 degrees. That is 0. Okay. I cross K will become minus J because K cross I is J. So then I cross K will be minus if you flip the two. Okay, then the sign becomes, so this is minus J. I cross J is K, so J cross I then will be minus K. J cross K will be I. Okay. So then at the end you'll get this will be minus 1.6 times 10 to the minus 13 coulombs times meters over second. And for the vector, you'll get, so we'll put I in the first one, 3.2 I. Okay. And these two are minus, so minus 2.4 J minus 2.0 K direction. Okay. So you can just, and then this is in Tesla. So Tesla here at the end, okay, for the unit. But these three units together, they make the units of newtons. So you can also write as this is going to be minus 1.6 times 10 to the minus 13 newtons. Okay. times this vector. All right, so this is 3D vector, so we can just leave it there. Or if they ask you for the magnitude, then we can do the x squared plus y squared plus z squared square root, right? And then multiply by this for the magnitude. All right, so this is the first one. Let's go back to this slide. All right, so the SI unit for magnetic field is Tesla. However, there's a unit that has been used a lot. It's called Gauss. Okay, so Gauss is a smaller unit than Tesla. One Gauss is only 10 to the minus 4 Tesla. Okay, so G, if you see G, capital G, that's for Gauss. Okay, capital T is for Tesla. All right, so here are some of the magnetic field that you might see reading textbook or from the daily life. So the Earth's magnetic field is only 0.5 Gauss, so it's a relatively weak one. A biomagnetic is about 100. Okay, sunspot is about 1,000 Gauss. Okay? And then the MRIs, they are stronger, so 2,000, 15,000. Okay, the strongest man-made magnetic field is 6 times 10 to the fifth. Okay, so that's about 60 Tesla. Okay, all right. So in natural magneta, a magnetic neutron star formed in a supernova explosion that is actually a very strong magnetic field, 10 to the 15. Okay. All right. So when we talk about the magnetic force, okay, so magnetic force is the cross product V and B and times Q. So in that sense, we can actually use the right-hand rule to determine what will be the direction of the force. Okay, so because F is equal to V cross B and then times Q, so then this can be applied. The right-hand rule can be applied here. So there's a couple right-hand rule in this topic under this topic, so we'll call this as right-hand rule 1. Okay, so right-hand rule 1 says to determine the force of the magnetic field, you first line your 4 fingers in the direction of your velocity of the charged particle. So in this case, in the green arrow, and then you curve your 4 fingers towards the the magnetic field. Then the thumb is pointing in the direction of the positive charge, in the direction of the magnetic force experienced by the positive charge. Okay, so in that case. And so this right hand rule is for positive charge. And if you have minus charge, you can still do the same thing, but at the end, you flip the direction of the force that you determine. Okay, so if this will be a negative force, then you flip it. So then the force will be pointing downward in that sense. Okay, so this is right hand rule. So F. So first, line your 4 fingers in the direction of the velocity of the charged particle, and then curve the fingers towards the magnetic field. Okay, and the thumb points in the direction of the magnetic field experienced by the positive charge. All right, so let's take a couple of practice here. Now, as you see, if we are discussing about the force, the magnetic field, and the velocity, right? So these are 3 vectors. So then a lot of times we all deal with 3-dimensional geometry here. So in paper, we only have a plane, right? Which means X and Y. So then in order to introduce the Z direction, so these are the 2 notations we typically use, okay? So for a dot, like dots, that represents the direction of the vectors out of the paper. For cross, that is into the paper. Okay, so perpendicular to the paper, into the paper, and dots perpendicular to the paper, out of the paper. Okay, so in this case, the in figure A, so the magnetic field represented by the dots here. So they are out of paper, so that means B out. And the bottom here, cross, that means magnetic field inside the paper. Okay, so you see dots are cross. or axis. So however you want to call. So sometimes textbook will just use dots or axis. Sometimes they use dots with a circle around each dot, okay, or a circle around each x. So in that sense, you see, if you see that, that also means the pointing out of paper or pointing into the paper. All right. So then, yeah, now let's get to the practice side. So for these three scenarios, it's asking what's the direction of the velocity of a negative charge. So again, this time you're looking for direction of the velocity, okay, but you're going to use the right hand rule. So you're going to line your thumb in the direction of the force, okay, and then your four fingers are curled in the direction of the magnetic field. Then you can tell what will be the original direction of the velocity, right? Because velocity originally and then curved towards the field in that sense, okay? So you'll just have to straighten your finger after you line the force with the thumb and then the four fingers with the direction of the magnetic field. And because this is a negative charge, so then at the end, you'll flip that direction of velocity, okay? All right, let's take a look at the first one. So direction of the force upward, B field is pointing out of paper, so towards you, okay? So that means originally, so now you straighten your four fingers. The original direction of the velocity is in the to the left, right? For a positive charge. Okay, so then in this case, because it's negative charge, that means the original direction will be in the to the right. Okay, so A to the right. All right. And you can also practice this. You can just pause the video and then practice B and C and then come back. Okay. So we'll take a look at the B scenario. Okay, so direction again, in that direction, your B field is in that direction. So you're going to curl it around like that. It's a little bit weird, but the four fingers now pointing to the right. So that means originally you straighten it, it's pointing towards you, right? So that means out of paper. But this is a negative charge. So it actually originally go into the paper. Okay, so we are going to say it goes inward originally. Inward. Okay. Now for C, this is the direction, thumb in the direction of force. Okay. Now the B field goes in there, so that means you curve it in that direction, the four fingers. So original direction of the four fingers is upward, right? But this is a negative charge, so that means originally it's downward. Okay, so you're going to say downward for the original velocity's direction. Okay, so at the end, for A is to the right. For B, the velocity was pointing inward, and C, the velocity was pointing downward. Okay, so those are the answers for A, B, and C. All right. So just as we did for the electric field, so the same thing we'll be doing it to the magnetic field. So we then, in this case, we also use field line to represent magnetic field, but because it's magnetic field, so we call them as magnetic field lines. Okay, so magnetic field lines, okay, that's the ones we use to visualize the direction of the magnetic field. Okay, so again, the density of lines indicate the strength of the field, and the direction is indicated by the arrows. Okay, so by definition, the magnetic field lines exit from the North Pole, okay, and then enters at the South Pole. Okay, so that's what you would have. So for a magnetic field, you actually have, or in this case, so you have the lines coming out of North Pole here and then goes into the South Pole. But inside the magnet, the field lines goes from the South Pole to the North Pole. Okay, so the magnetic field lines are closed loops. On the other hand, the electric field lines are not, right? So if you have positive charge and negative charge, then it always goes from positive charge to negative charge, okay, in a sense. It doesn't go back. But for magnetic field, lines, they are closed loops. Okay, so that's a little bit different here. Okay, so there's like bar magnetic. Usually that's what you see. There's also like the U-shape magnet. Okay, also called like horseshoe magnet. So in that case, you have south pole and north pole. Okay, so it's basically you have a bar magnet, but you bend it into a U shape. Okay, so the field lines goes from south pole to north pole, right? So in this arrangement, then you have strong field lines on one side, but not on the other side. Okay, so the application of that would be like a refrigerator magnet, right? Which it can just attach to the fridge on one side, but not the other side, because on the other side you have a very weak magnetic field. Okay, so then on the back side here has stronger magnetic field. All right. The magnetic field lines, they do not cross. Okay, so that means you don't get two magnetic fields at one location. If you do, they end up with, because they add up, right? Being as one single one. Okay, so that's what happens. So they do not cross. All right, so magnetic field lines, again, for biomagnetics, okay, it goes from the south pole and it enters the north pole. Inside, it goes from the south pole into the north pole. If you have two of them, the two poles close to each other, then you get more lines. So lines represent magnetic field strength, density is proportional to the strength. If you have the same pole close by each other, then you'll get a zero field in the middle because they repel each other. Okay. So these are also just similar to the field lines produced by charges, negative charge and positive charge in that sense. All right, so charged particles experience magnetic force. So that means if you have a charged particles moving inside a magnetic field, then its trajectory will be deflected or deflect or affected in that sense. So influenced by the magnetic field. However, the magnetic field, because it's the F equal to V cross B. So that means the force is just like K equal to I cross J, right? So I, J, K are perpendicular to each other. So that means actually F is going to perpendicular to either V or B, but V and B might not necessarily perpendicular to each other. Okay, so because they might have an angle that is not equal to 90 degrees, but the force is going to be perpendicular to the velocity and the B field. So basically, the force is going to be perpendicular to the plane that the velocity and the magnetic field makes. Okay, so in that sense, the motion of the charged particles in the electric field and in the magnetic field is going to be a little bit different. Okay, so in the electric field, it's always going to be experiencing the force of the electric field. So then the trajectory, in this case, if V is crossed, it's perpendicular to the E field, but it will be still deflected. Okay, so this is just like projectile motion. In this case, if V is perpendicular to B initially, right, then force is going to be perpendicular to B field. The force is always going to be perpendicular to the V, the velocity. So then the magnitude of velocity will not be changed, but the direction of the velocity will be changing all the time because the force is perpendicular to the velocity. Okay, so the velocity, its magnitude is not changing, but only the direction will be changing. So this will be then like a circular motion. Okay, so if you have a charged particle, original velocity is perpendicular to the B field, then it's going to have a circular motion. Okay, uniform circular motion in that sense because the velocity magnitude is not changing. If your V and B are originally not perpendicular to each other, right, then the V can be resolved into two components. One is parallel to the B field, the other one is perpendicular to the B field. So for the direction that is perpendicular to the B field, then you'll have the circular motion. For the direction that is parallel to the B field, so then it's always going to move a certain distance from the original position. If it goes one circle, right, and then it moves, so it will be displaced slightly in the direction of the B field. So as a result, the velocity of the charged particle is magnitude is not going to be changing, but its position in the axis parallel to the B field is going to be changing. But in that case, it's a uniform velocity, okay? Because the B field force on that component will be zero because V and B are perpendicular to each other, okay? And then V and B, the force on that component will just change the direction, okay? So this is then will be having a kind of helical path, okay? And then going in one direction. All right. So the interesting phenomenon happens like for auroras if you go to either the South Pole or North Pole during its winter. And you guys can click on this link here. It will direct you to a video that shows how the aurora happens. So basically, the charged particles from the sun reaches the Earth's magnetic field will be deflected, and then they are driven to either South Pole or North Pole, and that emits lights. Okay, in that sense. All right, another application of this is called the velocity selector. Okay, so you can have a bunch of the charged particles that are moving with different velocities, right? So you can charge, say the same charge, the same ions, maybe like say argon ions or whatever, but they might not necessarily be at the same velocity. But you can design a device so then after these charged particles moves through the device, only one specific velocity will be picked. Okay, so this is the device is called velocity selector, where you have an electric field and magnetic field. They are perpendicular to each other. So then the electric force and magnetic force of the charged particles are in the opposite direction. So once these two forces are equal to each other, so then the charged particle can move parallelly over there, okay, over this region. So it will not deflect it to the top plate or the bottom plate in that sense, okay? So then you can pick velocity by tuning the strength of the electric field and the magnetic field at the same time. So QVB equal to QE then, essentially. And then Q and Q will cancel, so VB equal to E, so V equal to E divided by B. Okay, so if you know your electric field and magnetic field, then you are certain what velocity the charges with certain velocity will come out. Okay, you can calculate what would that velocity be. Okay, so that's called velocity selector. All right, so let's take a look on the application of the velocity selector. So this guy says that the electron of kinetic energy 2000 EV. And this bar is blocking my view. Let me just stop because we are going to see the work on the paper anyway. Okay. All right. So it says initial kinetic energy. So that means 1/2 mv square is equal to 2000 electron volts. Okay, so that's the units for energy. Passes between parallel plates that are 1.0 centimeter apart and kept at uniform electric field and magnetic field. Okay, so you will have a something like this electric field, and then magnetic field. Let's say I think I show in the figure here. Okay, so going into the paper. Okay, so X cross. You can memorize this. I think I forgot to mention, but you can memorize that the cross or the dots as like an arrow going away from you or going into you. If you see dot, right, that means the head of the arrow. So you will only see one dot that's coming towards you. If you see the X, right, that's the tail of the arrow that is going away from you. Okay. All right. So B field, B is going into the paper, and then this is the E field. Okay, so this is 1 centimeter apart, 1 centimeter. E field is equal to, so it tells you E field is equal to 3.0 times 10 to the fifth meters over volts over meter. It's asking you what's the strength of the uniform magnetic field. Okay, so at the end of the day, when this particle, so electron, okay, so electron and positive here, so then E field will be going in that direction. So QE then is equal to QVB. Okay, so you can see which way the original velocity could be, right? B field is going into the paper, force is going downward, and so you're curving in that direction. So fingers are going towards the left, so that means original velocity will be in this direction to the right, okay? Because it's a negative charge. Okay, so these two will equal to each other, so QE equal to QVB. So Q and Q will cancel. You are looking for B, so then B equal to E over V. Okay, so you just need to figure out V, the velocity, right? So from here, you will be able to figure that out. So the velocity V is going to be equal to, so 2 times 2000, right? 2 times 2000 electron volts, 1.6 10 to the minus 19 joules, and divide by the mass, right? The mass of electron is 9.11 10 to the minus 31 kilogram. That equals to the square, right? So you take square root of that. So that gives you 2.65 10 to the 7 meters per second as the speed. Then goes here, you can find your B field. So that will be 3.0 times 10 to the fifth V over meters divided by this guy, 2.65 10 to the 7 meters per second. So that tells you that B field is going to be 1.13 10 to the minus 2 Tesla. Okay, so that's your B field. So calculate this one first, then calculate that. All right. So the separation of this doesn't matter. Okay, we don't use it at all. All right. So because as the charged particles enter the magnetic field, so only the velocity's direction will be changed, but this guy will be the magnitude will not be changed. So then if you have the V perpendicular to the B field initially, so then you have a circular motion, right? So you can measure what will be the radius of this circle, and you can use that information. Actually, you can determine what will be the mass and the charge ratio for this guy. So using this, the mass spectroscope can be designed. Okay, so this is what happens. All right. So this is what you can do. Okay, so the force is equal to, according to Newton's second law, is mass times acceleration. Now the force is coming from the magnetic force. So originally V and B are perpendicular to each other. So then QVB sine of 90. Okay, so then just QVB. The acceleration of this circular motion will be V squared over R. So M times V squared over R. So then R, the radius, is equal to mv over qb. Okay. So if you know V, okay, which is you can have this mass spectroscope work along with the velocity selector, right? So if you have velocity selector, you can know what will be the charged particles initial velocity here. So then the B field, you'll probably measure the strength. So then the ratio of the mass and the charge can be calculated. Okay. So the mass spectroscope is useful when you have different isotopics, oh, what's that word? The elements have slightly different mass, right? Isotope. Oh yeah, isotope, I think. Different isotopes, okay? So like for hydrogen and deuterium or the H and D for the chemical symbols. Okay, or carbon 12, carbon 13, they are different masses, but they are the same element with the same charge. Okay, all right. You can also calculate what will be the period for this guy. So 2 pi r over v. Okay, so then that's 2 pi. So r is going to be this getting into the equation here. So then it's 2 pi m over qb. Okay, then in terms of angular frequency, which is 2 pi times the frequency 1 over that. So then angular frequency will be q over m times the b field. Okay, so you can calculate the angular frequency, and then in terms of the magnetic field, you can get the ratio of the charge and the mass. Okay, so you can see for different isotopes, then you'll get actually different radius. So that's how you can tell which one is which, okay, by using a mass spectroscope. Okay, so typically, basically, this is what I've been talking about. So R equal to mv over qb. Okay, so for uranium 235 and 238, so you can separate them. Okay, by having their initial velocity being the same and then going through a mass spectroscope. So here you'll probably have a velocity selector and then a mass spectroscope. Okay, on mass spectrometer. Okay, so let's take a look at a real example here. So it says find the radius of the orbit when an electron. It's blocking here, so I will stop sharing so I can see the first line of the problem here. Okay. So it says if you have a proton and electron going through this device, okay, so what will be the radius of the two? All right. So you're going to apply the same equation here in this case. So the equation to apply is R equal to mv over qb. Okay. The q is the same, one is positive, the other is negative. Okay, so for the radius, we are it's a scalar quantity, so we don't care about the signs. Okay, so we can calculate. It gives us the velocity and B field. Okay, so the mass and the charge for the electrons and protons, they are fundamental elements, they are constant. Okay, so for a electron, of electron, R sub E is mass of electron times this V times E times B. Okay, so mass 9.11 times 10 to the minus 31 kilogram. Velocity is 6.57 times 10 to the 5th meters per second over 1.60 times 10 to the minus 19. And the B field 0.86 Tesla. Okay, so this will give you 4.28 times 10 to the minus 6 meters, which is 4.28 micron. For the proton, let's do R sub P. So mass of P, proton, and then E is the same. 1.674 10 to the minus 27 kilogram. 6.57 times 10 to the 5th meters per second over 1.60 10 to the minus 19 and 0.86 Tesla. So that will give you 7.87 times 10 to the minus 3. Okay, so this is like millimeter, this is a micrometer. Okay, so you can see if they have the same charge, different masses, they will have different radius when they go through the mass spectroscope. Okay. All right. So one more application. Let's go back to the slide. The magnetic field and the charged particle is called the cyclotron. Okay, so cyclotron is a device used to isolate the charge of the particle, charged particles. Okay, so what you have is here magnetic field in these two D-shape areas, and then in between the two D shapes, there's a electric field. Okay, so that is connected to the electric signals. Okay. So when the charged particles are in between this, they will be isolated, and then they are having just circular motion in the D shapes where you have a magnetic field. And then once it reaches to the other side, you can flip the signal. So this is AC signal. Okay, so the frequency is used is the related to the charge and mass and the magnetic field, okay, determined by those three. So you can again calculate this. So maybe we can go a couple slides backward. Okay, so in this case, so the frequency, right, for the charged particles inside the magnetic field is only related to this, okay, Q, M, and B. Okay, so by tuning that, then you always have the charged particles being oscillate, okay, when they are crossing the gaps. Okay, so at the end, you'll get a relatively large velocity of the charged particle that can come out of this exit over here and then hitting the target. Okay. All right, so that's the cyclotron. We'll stop here for today, and then we'll come back for the next lecture. Okay, so see you guys. Bye.